And one of the ways that you calculate you calculate the chi-square statistic is just plug the numbers here into this formula. Okay, this formula on the right, that's one approach. This is probably the most straightforward approach. Just plug in the numbers, you obtain a chi-square, you read it off in the statistical table, you're done. Okay, again, you have a 2x2 table, which is presented like this: exposed and unexposed, DHN, like that. And then you plug in the numbers into this table, into this formula, you obtain the chi-square, you read it off in the statistical table. Now, but then the question is, when should you be using the chi-square in the first place? Okay, so earlier we said that you use the z-test if the samples are independent. And one of the reasons why the chi-square test is more popular than the z-test is because it does not require you to only use this test in the context of independence, right? It's more flexible in that way. So you will see that you'll find chi-square tests more often in papers, in different analysis, okay? The other thing is that the chi-square test is essentially compares the proportion using the odds framework. And like it's easy to take this 2x2 table, calculate the odds ratio, and you get an inference, okay? But there's another way of calculating the chi-square test. And often this is the approach that is taught, or let me just say, this is another approach that people frequently teach. And the way that this approach is done is that you think about a scenario where you have a set of observations and then you have a set of expectations. Now, so if you have an observation and you want to imagine a situation where the exposure did not lead to the disease, okay? If you imagine a situation where the exposure did not lead to the disease, then you ask yourself, if you want to create a 2x2 table where the exposure does not lead to the disease, what will the 2x2 table look like? And I'll show you that in one moment using an example. Okay, all right, so you're interested in examining whether intake of sugar sweetened beverages, SSBs, is associated with obesity among school children. All right, you have 863 obese children, you have 637 non-obese children in your study, and then you ask them about their consumption of SSBs in the last week. The first thing you do is that you fill out your 2x2 table, which is the one on the left, of observed numbers. So you know the number of people who were obese, the number who were not obese, right? The number who were exposed, the number who were not exposed. And then you calculate the proportions, the row-wise proportions, okay? So among the exposed, 60% of them became obese. Among the unexposed, 55% of them became obese, right? So you begin to ask yourself, does exposure lead to the outcome in this case? But there's a total, which is 57.5%. In this scenario, what we did was that we took this 57.5%, you apply it to this 750%, okay? You apply it to this 750%, this is 750, and then you obtain 431. So you're imagining that if SSBs did not lead to obesity, how many people would have still become obese among the 750? That is 431. Okay. If not having an SSB does not increase the risk of obesity, how many people would have still had obesity? That is 431. So you obtain 431, you subtract that from 750, 319. So these are the observed, this is observed table, and this is the expected table. Is that clear so far? Does anybody have questions at this point? This approach of the chi-square implements the test in 3 steps. Step 1 is to fill out the 2x2 table. Step 2 is to fill out, step 1 is to fill out the 2x2 table of observed numbers. Step 2 is to fill out the 2x2 table of expected numbers. And the way that we usually fill out a 2x2 table of expected numbers is to, one, assume that there is no effect. And the way that you will do that is you take one of the percentages, it could be this 57.5, and then you apply it here and assume that everybody who was, who had SSBs would have had the same proportion of them that would have become obese, that would have had the outcome. And then you subtract like this, okay? I don't see any new hands up, so I'm going to assume that it is clear at this point. I'm going to take one question.
So someone wants clarification on the 2x2 table for this example.
Okay, thank you very much, sir. And I would like you to go over the table again because you not rather fast. And it's not so clear. Thank you.
It's not so clear. All right, thank you. All right, so let me go over this 2x2 table again. So first of all, one thing to note is that this question is not complete, right? We had 863 obese children, that is here, 863. We had 637 non-obese children, that is 637, okay? 637 non-obese children. Then we had, we were told that 60% of the obese children, right, of the 60% of those who had SSBs became obese, okay? So like I said, the question is not complete. So half of the children had SSBs, half did not have SSBs in the last week, and you have 1,500 people in the whole population. So essentially, you start with the numbers on the flanks. You start with the totals. So we have 1,500 people. You have 750 who did not get SSBs, 750 who got SSBs. Of those, 863 were obese, 637 were not obese. So having known those numbers, right, you can then go ahead to fill this out, right? And you're told that maybe 60% of the obese people received SSBs, 55. So the information that you have to then calculate that you're not giving, ideally, is only this number, for instance. But assume you have this 2x2 table as a given, this of observed 2x2 table. Then you want to obtain this 2x2 table of expected numbers. And this is where it becomes a bit tricky, okay? You take one of these percentages, it could be 57.5%, okay? You take one of these percentages and you multiply it by the 750, okay? If you multiply 57.5% by 750, you will get 431. Okay, if you the same thing here, you multiply by 750, you get 431, and then you can subtract 431 from 750, you get 319. So if you add it across, so the numbers in the totals here become a little different due to approximation. Okay, but it doesn't matter, it's just one difference, so it won't affect the results. So if you add 431 and 431 now, you get 862. You add 319 and 319, you get 638. Okay, I'm waiting to see if anybody else still has questions.
No questions in the Q&A.
Okay, all right. So that's step 1 and step 2. Step 3 is to now plug the numbers into this formula. Okay, and this formula is basically you set the two tables by them on we set the two tables side by side like this. You take 450 and 431. Okay, you plug it into this formula, observed minus expected divided by expected, right? This is squared. You take 300 minus 319 divided by 319. You take this 413 minus this 431. Let me use this pointer that's colored so you can. Okay, so you take this 413 minus this 431. So after doing all of that for each of the cells, for each of these 4 cells, okay, then you add them all together. When you add them all together like that, you will get this number 3.841. Okay, let me take that again. You take, if once you filled out the table of observed numbers and the expected numbers like this, you take the numbers in each cell, 450, 431, and you subtract them from each other. You square it, you divide by the expected number, the corresponding expected number. You do the same thing for this cell, 300 minus 319. You divide it by the corresponding expected number. And then you do that for the other 2. Okay. And the rest of it is just math. When you calculate it, you get 3.841. Okay. So you get 3.841 here. Now, the other question is then the degrees of freedom is the number of rows minus 1, number of columns minus 1. Here, this is a 2x2 table, and the degrees of freedom is 1 here. So if you plug this into the statistical table calculator, you get a p-value that looks like this. Does anybody have questions? Or is this perfectly clear? We can just go on. We're doing great. So I'm going to take a question.
Hello?
Yeah, hi, Shadrach. Yeah.
Yeah. I was saying, like, now, if the outcome, let's say if the outcomes was like underweight, normal weight, and overweight,
okay,
you still use a chi-square?
You can use a chi-square. And you can set it up exactly like this if you want to do it by hand.
Okay.
Yes.
Okay.
So, but you know, you have to remember that is no longer a 2x2. That is now a 3x2 or a 2x3, depending on how you choose to describe it. I think it's 2x3. Yeah. Okay.
So how will you calculate the degrees of freedom for the 3x2 parameter? Let's assume you have.
The degrees of freedom is always here. The number of rows minus the number of minus 1, number of columns minus 1. So if you have 2 rows, 2 minus 1, 3 rows, 3 columns, 3 minus 1, you multiply it together.
Okay. Thank you.
Yeah. Okay. All right. So more questions.
Okay, thank you. I wanted to ask the final calculation we just did.
Yeah.
The last part where we have 338 for the from the observed table. I think I just want to be clear if that was a mistake. Like it's 337 in the table, but we have 338 in the calculation.
This one and this one.
No, I mean row 3, column 3. No, the next one on top, 337 for 45%. In the observed table.
Observed table. This one.
Yes, exactly there. So and when it was captured in the calculation, it's written 338. I just want to believe it's a mistake. The last
yes, that's a mistake. Yes, it should be 337. Okay. You're correct.
Okay,
yes.
Thank you. Yeah.
Thank you.
Hello, sir.
Yes, please go ahead.
I just want to ask a question pertaining to the observed and the expected.
Okay.
Is it that the expected will have been given in a scenario? and we are now comparing with our own observation from our data.
No, so the observed will be given, okay? The expected, you have to make assumptions about. So the reason why I keep making this red is because this is a number that we used to calculate the expected. So you essentially take one of the proportions that you have, okay, and you plug that into your formula. So in this case, we took 57.5 and we multiplied it by this 750, okay, and we obtained 431, and that's our expected for this proportion.
Okay.
And then we subtract 750 minus 431, we obtain 319.
Okay.
Then we take the same 57.5%, the same number, same proportion that we chose. This might not be 750, might be something else, depending on the question, might be 800. But we multiply it by 750 in this case, and we obtain 57.5. Sorry, and we obtain 431, sorry.
Okay, yes.
And then we subtract again here. Then we add 431 and 431, we obtain 862, 319, and 319, we obtain 638.
Okay, I get it.
Okay. Yep.
Okay, so that means, okay, 57, then the remaining percentage will fall for the, is the obese and the non-obese, so the remaining percentage will fall for the other side.
For this other side, yes, exactly.
Okay.
Okay.
All right. Thank you very much.
You're welcome. All right, so let's take a break here, and we'll take a 4-minute break, and then we'll come back in 4 minutes time, and then we'll go ahead with the rest of the class. All right, so let's get started. Before the break, we were looking at z-tests and chi-square, and we showed how to look at chi-square by hand. All right. So now what we're going to do next is that we are going to just very quickly show you that you can also do chi-square using software, right? In SPSS, you can do chi-square. And if you did, this is what it would look like. This is what the output would look like. Now, if you attended the SPSS lab, you would have already seen this output, because chi-square, we've already gone through chi-square in SPSS. But this is what the p-value would be for this particular output, and this is what the chi-square statistic will be. So let me ask a quick question. So in this particular situation, it's the resident hours data set that we're looking at. You're comparing whether males or females were more likely to work more than 80 hours, assuming no confounding. What do you conclude? Who is going to take it for us? Anyone want to give it a shot? You have a p-value of 0.25. You have a chi-square of
Hello.
Yes, hi.
Yeah. Based on this, we'll fail to reject the null hypothesis.
Excellent.
So it means that, yes, based on the p-value of 0.251, so it means that the gender is not associated with working for more than 80 hours.
Excellent response. Gender is not associated with working for more than 80 hours. Okay. So now let's keep going. So there's some reasons to be cautious about the chi-square test, right? It does not tell us about how large the difference is. It's also only valid if the sample size is large. So if you have a small sample size, the chi-square test is going to be wrong. And this is often a situation where a lot of people make mistakes, right? If the sample size is less than 50, for instance, then you should use the Fisher's exact test. And we're not going to teach you that, but if you're going to use software, it's easy to implement. You can always check that on Google. Okay. But the other very key point that you should remember is that the chi-square is sensitive to small expected counts. Okay, the chi-square is sensitive to small expected counts. So if say you have your observed numbers, and then you have your table of expected numbers like here, and one of those, the numbers in your cell is less than 5. If one of the numbers in your cells is less than 5, then the chi-square might not be valid. And the reason why you have a situation like this, okay, is often that it's either the exposure has an almost perfect effect on your outcome, which is kind of rare, where everybody who has the exposure will have the outcome. All right. If everybody who has the exposure will have the outcome, you will not be able to use a chi-square test in this case. Okay. Or if nobody who has the exposure has the outcome, in which case, when you do the expected numbers, one of the cells becomes so small, it will be difficult to use a chi-square test in this case. There are some modifications that you might do, which we don't teach, but just be aware that this is a challenge, and there's not often like agreement on what you should do among researchers. Some people will say, add numbers here, or add numbers to all of them, or some people might say, just abandon it and use another test. But just be aware that this is a challenge. So let's move on to logistic regression. Okay. So